hear me. I believe that you guys can, but hopefully you guys can. Okay, so let's talk about question number 2. So question number 2 asks us to find the point on the line y equals 3x plus 4 that is closest to the origin. Alright, so I need to define what our origin is first, and if you guys don't know, so, whoops, it's blue for some reason. So on our Cartesian plane here, and we're going to label the axes, the origin is basically the center of our Cartesian plane, or the coordinate 0, 0. Okay, so they're asking us, given our line, so this is not actually the line, but I'm just doing for illustration, given our line, which is y equals mx plus b, find the point on the line here that is closest to our origin, right? So along this whole line, which point on our line is closest to the origin? Okay, so that's what they're asking us to do. So, you guys can obviously graph this line and visually try to locate it, but there's a computational method of doing this, okay? And it requires us to know what the distance formula is, okay? So the distance formula is d equals the square root of x2 minus x1 squared plus y2 minus y1 squared, okay? Where x1, y1 is 1 point, and x2, y2 belong to R2, okay? So basically the distance formula helps us to calculate the distance in units between two different points, okay? So we're going to use this formula to calculate the closest point on our line to the origin, okay? So let's say that let point xy be a point on y equals 3x plus 4. Okay, so if xy is a point on y equals 3x plus 4, the distance from that point to the origin is as such. X minus 0 squared, right? Because x1 is going to be 0 and y1 is going to be 0. So, and x2 is going to be x and y2 is going to be y minus 0 squared. Okay, so this is the distance in units between our point xy on our line, y equals 3x plus 4, from that point to the origin. That's the distance formula, right? So if we were to simplify this, we would get d equals the square root of x squared plus y squared. Okay. So the second thing that I want to do is I want to plug in y, right? So we know that y equals 3x plus 4, so I'm going to plug that in. So if we plug in y, we get x squared plus 3x plus 4 squared. Okay. And if I were to simplify this, it would be the square root of x squared equals, let me just write out the entire thing. So I'm going to expand this bracket. So it'll be 10x squared plus 24x, oops, plus 24x plus 16. Okay, so I expanded this bracket and then I added everything together. And now we have found a distance formula from this point on our line to the origin. However, that's not the only way to describe what we see here, okay? We have created a new function that calculates the distance of any point on the line to the origin, okay? So now that we have found a function like this, we're going to optimize this function by finding its derivative and finding when the derivative is equal to 0. And when we find that optimized point, we have found basically the point which is closest to the line, or to the origin, okay? And I'll explain a little bit into detail why, all right? So the first thing that I'm going to do, now that I have found our function, is I'm going to get rid of the square root. So I'm going to square both sides, okay? And the reason why I do this is so that our derivative is a lot simpler to calculate and we don't need to worry about it because the minimum of d and d squared is going to be the same, okay? So now that I'm going to find the derivative, I'm going to prime this. and we're going to find the derivative of this. So it's going to be 20x plus 24. Okay. All right. So let me recap what I just did. So first of all, I defined a function which measures the distance from any point on a line y equals 3x plus 4 to the origin. And then I reasoned that if I were to find the critical point of its derivative, I'll be able to find the point on the line that's closest to the origin. Okay, so then now I did the derivative, and I made it easier to calculate the derivative by squaring both sides, because I reasoned that the minimum or the critical point of d squared and d are going to be the same. Okay, and it's going to be the same. Right, so now that I found the derivative, this is what it is, and we're going to set d squared prime x to be equal to 0. And to do that, we're going to calculate the value of x, which will make this equal to 0. So then if 20x plus 24 is equal to 0, then we get 20x minus 24. We get x equals negative 12 over 10. And then be negative 6 over 5. Okay? So, why did I try to find the critical points of our derivative? Okay? So when we set the derivative to be equal to 0, we're locating the points of our original function where there's a horizontal tangent. And there's a theorem in calculus that states that the horizontal tangents on a function relates to either a maximum, a minimum, or a saddle point. Okay? In this case here, we only have one value of the function, which is makes the derivative equal to 0. And this is the only critical point. Okay? So we're going to look at this critical point and identify whether or not this is a max or a minimum. Okay? And most likely it's going to be a minimum because of the nature of how our derivative works, or how our original function works. Okay? So now that we have found the value of, or the critical point of interest here, which makes our derivative equal to 0, we're going to plug it back into our original function. Okay? So our original function is our line function here, because we have now identified the value of x, which is closest to the origin. Okay? So now we just need the y coordinate, right? So we're going to plug x equals negative 6 over 5 back into y equals 3x plus 4. Okay? So we have found the minimum point, which is negative 6 over 5, and now we're going to plug it back into our line equation. So y equals 3 times negative 6 over 5 plus 4, and this would be negative 18 over 5 plus 4, which equals like 2 over 5. Okay, so therefore, negative 6 over 5, 2 over 5 is the closest point to the origin. Okay. So by optimizing this function, we have found the value of x, which is the coordinate for the point on the line that's closest to the origin. Okay. So in other words, when we are calculating for the derivative of this function, right? So this function measures the distance of every point on the line to the origin. Okay. So we're trying to find the critical point of this. We're trying to find the point on the line which makes the derivative equal to 0, which means that that makes the distance equal to its minimum. Okay, so when the derivative is equal to 0, the x and y coordinate of that function, I guess, relates to how the distance is minimum in our original function here. So that's the rationale behind finding the derivative equal to 0. Okay, and once I found the x coordinate, I just plugged it back into our line equation, and we found the y coordinate. And by doing so, we have identified the closest point to the origin. So the solution is correct. Work. Okay.